So we're getting a little bit away from geometric series a little bit and just kind of focusing on series in general for these next few things. We're going to start it off with a theorem. If we do have an infinite series, so this is just a generic one, n going from 1 to infinity over some sequence of values a sub n. Let's pretend that this series does converge. Then that automatically means that a sub n has to go to 0 as a sequence. Okay, so I hope this theorem is obvious, but let's at least talk about it a little bit. So if we know that the series converges, the only possible way for a series to converge is if eventually the numbers that you're adding are pretty much 0. Otherwise, the sum is going to be changing, right? So you have to have that the sequence values go to 0 for a series to be able to converge to a sum. Okay. From this, we get something called the nth term test. These tests, and there's going to be a lot of them over the next 8 or so sections, are very important. So this is the first of the tests that we're going to be using. The purpose of these tests is to see whether a series converges or diverges. What the nth... All right, sorry. I had to go back in the video because I was stumbling over my words so much. I just wanted to start over. So here we go, the nth term test. What the nth term test says is this. A series, n going from 0 to infinity, over some values a sub n, this thing diverges if the limit of the sequence a sub n fails to exist or is different than 0. Okay, this, for whatever reason, confuses students to no end, so I'm going to try to really over-explain this one. What the nth term test says is that a series diverges if the limit of the sequence values either doesn't exist or is different than 0. Okay, that's coming from this theorem up top, because remember, a series only converges if the sequence goes to 0. So if the sequence doesn't go to 0, it has to diverge. All right. From the nth term test, we have two outcomes. The first outcome is this. You calculate the limit of the sequence, and the limit of the sequence does go to 0. If that is the case, the test is inconclusive. Just because a sequence goes to 0 does not mean that the series converges to anything. That's not what this theorem says. The second outcome is that you calculate the limit from a sub n and it is not equal to 0. If that is the case, then you can say that the series diverges. But that is the only two outcomes of the nth term test. The nth term test never tells you if something converges. It only tells you if it diverges or if the test is inconclusive. Cool. Let's look at some examples. Let's start off with the infinite series as n goes from 1 to infinity of n plus 1 divided by n. Okay. If we look at the sequence on the inside of the series, the n plus 1 over n, as a sequence, n plus 1 over n converges to 1, right? If I plug infinity in for these n's and then do L'Hopital's rule, this converges to 1, which means that eventually we're just going to be adding the number 1 to my series over and over and over again. Well, if I'm adding the number 1 over and over and over again, then the series can't possibly converge. Thus, the series diverges. This series. Okay. Since the sequence did not go to 0, the series diverges. Let's look at one more example. Let's look at, this is a pretty good one. N equals 1 to infinity of -1 to the n plus 1. All right, so let's talk about this one in detail a little bit, because all this one does is just alternate +1, -1, +1, -1, +1, -1, forever and ever and ever. So the question is, right, does this actually converge to a sum? And the answer is going to be no. And the reason for that is because of the nth term test. If we just look at the sequence -1 to the n plus 1, this is going to be the sequence 1, -1, 1. So just 1, -1, 1, -1 forever and ever and ever. That never converges to anything. So this does not converge as a sequence. Because it doesn't converge to 0, thus the series diverges by the nth term test. Okay, so since the sequence of values does not converge to 0, the series has to diverge. All right, let's look at one that's inconclusive. So just one more example here. Let's look at the infinite series of, let's do 1 over n. Okay. So as a sequence, 1 over n does go to 0. But just because the sequence goes to 0 does not mean that the series converges. Thus, the nth term test is inconclusive. Okay. So if the sequence goes to 0, that means that we have to try a different test. It's only when the sequence does not go to 0 that we get to make the statement that the series diverges. Okay, so hopefully on the homeworks that's not going to be too confusing and that makes sense. There's still a bunch of definitions that we need to write down here for section 2 before we start looking at more tests in section 3. Starting off with a theorem. If we have a series A sub n that we know converges to a sum of A, and we have another series, B sub n, that we know converges to a sum of B, are convergent. All right. So let's just pretend that we have these two things. We have one series that converges to a sum. We have a different series that converges to a sum. Then we want to look at a couple of rules. First thing that we have is the sum rule. And this is very similar to the sum rule that we had for sequences in the last section. If we look at the sum of the individual terms added together, that's the same thing as just the sum of the individual series added together, like this. That, that is the same as just the two sums added together. All right. In other words, if you have two series that you know converges, you can add the two things together and it still converges. We also have a difference rule. I'm not going to bother writing this one out, but just put minus signs in place of all of this stuff. And then the third one is the constant multiple rule. So what the constant multiple rule says is that if you have a series where you have a constant times your sequence values, I hit that same button again. This converges to just that constant times the sum. In other words, if you do have constants inside of your series, you can pull those constants out. But that's it. Those are the only rules that we have. Notice that we do not have a multiplication rule and we do not have a quotient rule. So the sum of A sub n times B sub n may not be equal. How do you do not equal? Here, I guess. May not be equal to the two individual sums multiplied together. Same thing for dividing. Okay. From these three rules up here, there's actually some corollaries that we could write down. A corollary is just kind of an addition to a theorem. So here are the two additions. Every non-zero constant multiple of a divergent series diverges. Excuse me. So what this corollary is saying is that if you know a series diverges, there is absolutely nothing that you can multiply it by that's going to make it converge, except for 0. But that's kind of lame. So if something diverges, it doesn't matter what constant you multiply it by, it's still going to diverge. The second corollary, if you have one infinite sum that converges, and you have another infinite sum that diverges, then if we look at the sum and the difference of these two things, so a sub n plus b sub n, and also the sum of a sub n minus b sub n, both of these diverge. All right, so if you have one series that converges but another series that diverges, then the sum or the difference is also going to diverge. You can kind of think of it like diverging takes over from converging. Diverging is more powerful than something converging. Okay, good. There is a little caution to this that I want to write out. If you have a series that diverges and a second series that also diverges, then it is possible for the two series to be added together or subtracted and converge. Crazy, right? So if you have one that converges and one that diverges, and you add them or subtract them, it has to diverge. But if you have two that diverge, it is possible that you add them together and it converges. Cool, right? If you're super curious about that, just ask me during one of the meetings. I can show you an example. But this video is getting a little bit long. I only have one more example to do, so let's knock this out. So let's look at the infinite sum, as n goes from 1 to infinity, of 3 to the n minus 1 minus 1 all divided by 6 to the n minus 1. Okay, so like this. The question is going to be find the sum. All right. Usually, when I give you something like this on a test, the question is going to be, does this converge or diverge? And then if it does converge, find the sum. But in this case, I'm just going to go ahead and tell you that this does converge. Let's find the sum. If a question is asking you to find the sum, then your hint for that is to use geometric series. I would never ask you a question to find the sum of a series unless it's geometric. So this is geometric, or at least it's sort of geometric. We can use geometric series to find the sum. So let's do it. The way that you should always do these is that you should separate them out using the sum, the difference, or the constant multiple rules into geometric series themselves. The way we're going to do that is we're going to break this one down by dividing the top and the bottom by that 6 to the n minus 1, just like we did it before. So we're going to have just the first one to be 3 to the n minus 1 divided by 6 to the n minus 1. And that's going to be minus the next infinite sum of 1 over 6 to the n minus 1. Ah, geez. I flew way up there. Minus 1. Once I get it in the right spot. There we go. Okay, cool. All right, so we're just breaking up this infinite series. Instead of looking at it as one big fraction, we're separating it out into the two separate fractions. And now we want these to be individual geometric series, and they are. So both of these are going to be going from n equals 1 to infinity. When you take 3 to the n minus 1 divided by 6 to the n minus 1, because these are both to the same exponent, I can combine them together internally. That's going to be a 3 over 6, which simplifies down to be 1/2. And then that 1/2 is going to be to the n minus 1 power. That's going to be minus this other infinite series that's also going from n equals 1 to infinity. And this one I'll write as 1/6 all to the n minus 1 power. The reason I'm writing it like that is that now these are in that perfect format. Here we have two separate geometric series. This geometric series has the a value of 1, the r value of 1/2, and because 1/2 is less than 1, it converges. This also has an a value of 1, but an r value of 1/6. That converges. So that means that the sum of this series up top here is going to converge. This one is going to be a over 1 minus r, which is 1 over 1 minus 1/2, minus this other one is going to be 1 over 1 minus 1/6. Good enough. Okay, and then you just type all that into the calculator or fiddle with it a little bit, and you should get 4/5. So this series here will eventually converge to 4/5. Okay, so that's it for section 2. Section 3 is going to be just a couple more tests.